So our next speaker is Dr. Sabya Tiwari from UT Austin, and yeah, the floor is yours.
I'm audible, right? Yes. Am I audible? Okay. Thank you, Professor Ponce, for the introduction. So in this talk, in this lecture, I'll be talking about the quasi-degenerate many-body perturbation theory applied to the optical absorption and luminescence problem. So this is the summary of my slides. So basically, I'll talk about the first. I'll give you some introduction about the current theory and the light absorption and emission. Then I'll talk about the limitations of the current theory, which we will refer to as the CHBB. Then I'll introduce the quasi-degenerate many-body perturbation theory, and we'll apply it to some of the materials, and eventually we'll conclude. So first, the introduction. So how exactly this work started was that we all know that for optoelectronics are very important for the energy applications, and we need materials for optoelectronics. What we actually wanted to do is that since the material design space is very large and experiment cannot be performed on all of these materials, so the idea was that we will actually go theoretically screen some materials which are good for optical electronics and which are kind of can be used for future optoelectronics. However, the quantity that we use to quantify if a material will be a good absorber, emitter, will it be good for optoelectronics or not, is the absorption coefficient. However, when we delved more into the theory, we found that the theory for the calculation of optical absorption can be divided into two groups. One is for the direct gap materials, so materials whose band gap is direct, and these, for example, gallium arsenide. And then there are materials whose band gap is indirect. There is a different theory of optical absorption that is used, for example, silicon. Now, this is the preliminary of the theory of optical absorption. So if I think about like a system which is exposed to electromagnetic radiation, its total energy can be written as a summation of the non-interacting part of the Hamiltonian, the electron-phonon potential, and the electron radiation potential. The electron radiation potential is given by this expression here, as you have already seen in the first lecture by Professor Giustino. These are basically the creation and annihilation operators, fermionic creation and annihilation operators. V is the velocity transition matrix element, and these are the amplitude of the electromagnetic wave, and E is the charge. This is called the interacting electron radiation potential. This is the first order. The second term is the electron-phonon potential, which you know very well by now, comprises of the fermionic creation and annihilation operators and the bosonic creation and annihilation operators displacements. G is the usual electron-phonon matrix element, and H naught is the non-interacting part of the Hamiltonian, which is just the Kohn-Sham orbitals. Now, in the case of direct gap materials, what happens is that the electron hole pairs, so basically you shine a light on a material. This is how the band structure of a direct gap material looks. You have a valence band, you have a conduction band, and you can have a satellite conduction band whose energy is much higher than the lowest energy conduction band. So in this case, what happens is that the conduction band minima and the valence band maxima align at the same K point. Now what happens is that when you shine light, and if you remember from the previous slide that the electron radiation potential is proportional to the creation annihilation operator of fermion at the same K point, what basically it does is that it creates an electron hole pair. Now, if I assume that this state is basically what I call I naught, when these operators act on this I naught, what they do is that they create another many-body state where you remove one electron and you create that particular electron in the other orbital. So basically, in the other band, so you remove one electron from the valence band, you create it in the conduction band. And this is the representation for that state, which we call as the final state. Now what happens is that since this is possible because the photon energies is the same as the energy difference between the conduction state and the valence state at the same k point. And next, what we can do is that since we want to calculate the absorption coefficient, we need to obtain the transition rate. So basically, how many carriers I create per unit of time, that I can calculate very easily using the Fermi's golden rule. And this expression in general works very well for the direct gap materials. What happens in the case of indirect gap materials is that the situation changes in the band structure. So here, the conduction band minima and the valence band maxima are not aligned at the same k point. So the conduction band minima is at a k point, which we call k plus q, and the valence band maxima is at the same is at the k point, which we call as the k. Now, since photons do not provide extra momentum, what we need is something to provide this extra momentum, some kind of interaction. And phonons can actually provide this extra momentum. So how exactly it happens is that if you look at the electron-phonon interaction potential, is proportional to these creation and annihilation operators. So basically, you remove a carrier from C prime K and create that same carrier at a CK plus Q, while at the same time, you also create and emit a phonon. Now, when this state, so basically what happens if you think about this theory, the light first should create a electron hole pair at the C prime and C prime K and VK. And when the electron-phonon interaction potential acts on this many-body state, what it does is that it creates another state, many-body state, where basically your electron and holes are at different k points. This you can say is something which we call as the finite momentum excitation. And the many-body state can be represented using this picture. And since you might be thinking, okay, here the photon created an electron hole pair at a larger energy than the photon energy itself, but what you need to see at the end of this operation, the energy is conserved. Since the energy of this satellite state, basically this finite momentum excited state, is the same as the photon energy that we applied. So this is how the absorption in the indirect gap materials happens. Now, since there is already an extra interaction that we have in the system that you need to transition to the excited states, which is the electron-phonon interaction, the transition rate is a second-order perturbation. And here you can see that you need both these interaction potentials. So electron radiation first acts on the ground state, creates an intermediate state, and from this intermediate state, the electron-phonon interaction basically creates your final state, which is the finite momentum excitation. The vice versa process can also happen, that the electron-phonon creates the intermediate state, and then the electron radiation creates the final state. However, if you look at the denominator, is the intermediate state minus the initial state. So basically, this denominator is as big as the band gap. And in large gap systems, this contribution can be low. So the major contribution in large band gap systems or semiconductors comes from this first transition rate. Now, this is exactly what we call as the CHBB theory in the indirect gap materials. And this is actually a second order perturbation theory. And if you do more maths, and you have already seen this in the Wednesday presentation of Professor Kupakis, is that you can derive an expression for the change in the number of particles. And from this, you can obtain the dielectric constant and the absorption coefficient. If you look at this expression, you get these two terms, which are called the oscillator strength. And this expression was originally obtained by Cheeseman, Hall, Blatt, and Bardeen. These are the publications. The other thing it contains is the Bose-Einstein occupation. And eventually, this is the density of state, where you see that the final state energy has to be the same as the photon energy. So this is the expression. And the thing I want you to focus on are these two oscillator strength. which looks something like this. So they are a combination of the velocity matrix element and the electron-phonon coupling, and whose denominators are basically the energy eigenvalues of these various quantum states and the energy of the photons. This theory works particularly well, or I would say very well, for materials which have large indirect gaps. For example, or I would say the materials whose indirect and direct gap is very different. For example, silicon. So most of the absorption that happens in silicon in the visible range occurs through the indirect transition. And as you can see that this is the same as in the previous slide from Professor Kupakis' lecture, the CHBB theory works particularly very well and matches the experiments quite nicely in this regime. So, and I also want you to keep a note of this particular eta and the this particular expression. So what is the issue? Since we have a theory for the direct gap materials, and we also have a very nice theory for the indirect gap materials, which matches the experiments, the issue is this, and now we'll discuss the limitations of these theories. You've seen in the Monday slide of talk of Professor Giustino that if we use only the direct transition rate or the direct absorption formalism on silicon, so this is the absorption coefficient as a function of photon energy in silicon, dots are experiments, we are not able to recover the full spectra because most of the absorption happens through indirect transitions. When we add the CHBB theory of indirect transitions, we are able to recover the indirect part of the absorption. However, in the regime where the direct absorption is allowed, the indirect absorption expression becomes ill-defined. And these numbers which you see, 2 MeV, 10, 100, 500, these are basically the numbers for the eta that we have used in the previous expression. So CHBB theory becomes unphysical in the regime of direct absorption. Now, what happens in the case of, so you might say, okay, this theory works in the indirect regime for silicon. For the direct regime of silicon, I can use the direct absorption expression. However, a big problem happens when you have materials where the direct and the indirect gaps are closed, which we call as the quasi-direct materials. Now, in these kind of materials where the conduction band minima can be at the same K point, but there is also a satellite band whose minima is at the K plus Q K point at a different wave vector, basically the light can, photons can create an electron hole pair at the same K point. However, these same, the phonons can then kick in and they can create electron hole pair at a finite momentum excitation. So basically, they can take the electron from the highest, from the lowest conduction band and take it to a finite momentum. So they take the electron from the K, they take it to the K plus Q. So both of these can happen in practice in nature. And both of these will have contribution to the absorption coefficient. However, what happens is that, and why we actually saw that the theory becomes ill-defined, is because these two states have the energies quite close. And in the CHBB theory, the final state energy and this intermediate state energy appear in the denominator and they cancel each other. And if these energies are the same, this expression goes to infinity. And that's why the CHBB theory becomes ill-defined. So what to do? For example, we do have materials where this type of situation appears. And in the case of direct gap materials from the direct gap onset, they can also have indirect transition. So we do have this kind of a situation. And one of the prime examples of this kind of situation is germanium. So in case of germanium, the direct gap and the indirect gaps are different by 100 MeV. So that's a very small number. And when we apply the CHBB theory and also the direct absorption theory in germanium, and here we actually calculate the photoluminescence. So these dots are basically from experiments. The purple line is is what you obtain from the direct absorption. And the blue line is what you obtain from the CHBB theory. And you can see that both of them are unable to reproduce the experimental photoluminescence. Although the direct absorption obtains, at least predicts this particular kink in the PL correctly at the same energy, it's unable to reproduce this big chunk which comes from the phonons, while the problem of the divergence in the CHBB theory kicks in, and that basically shifts the entire PL spectra. Another question which we are confronted in these kind of, okay, we cannot obtain the PL spectra, but we can, of course, in a quasi-direct gap material, if I just do direct, forget about the very small indirect part, I would still recover the optical absorption coefficient more or less correctly. The question that comes in is what happens? So this more physical question is what happens to the transition rate? So is the transition rate or the optical spectra only comprised of the direct contribution, indirect contribution, and when we have to bring them together, do we just do a simple addition? So these are the questions with which we started working on the quasi-degenerate perturbation theory. So why quasi-degenerate? The reason is that once these band gaps come close, the direct and the indirect gap, the materials basically have this degeneracy problem. However, this degeneracy is not defined at one energy, because since you have a continuum of energies, there is a range of energies over which you will have degeneracy. At the same time, this is a numerical thing. So if you perform a calculation, you will never find perfect degeneracy in most of the cases unless they are symmetric. So what happens in the quasi-direct gap materials is that basically you have these electron hole pairs which are at the same K point and which are represented by this kind of state become degenerate with the finite momentum excitation, which are represented by a state like this. So how do we get rid of this degeneracy problem and come up with a theory that basically works for the entire regime of the photon energy? And that's where we started working on the quasi-degenerate many-body perturbation theory. So the idea is very simple. Since we have a continuum of states across the energy, which can be degenerate, what we can do is that we can define a bin or a range of energies, which we consider that, okay, within this, I assume that all the states which are within this delta E are basically degenerate. So here you see a representation of that. So here we plot these states which are finite momentum and zero momentum and finite momentum excitations in blue and red. And if we actually start placing them with their energy values, we will see actually a picture something like this. Within this, we actually take a bin. For example, here we call it delta E. And all these states which are inside this bin, we basically bring them to one single energy state. When we do this operation, so basically when I'm changing the energy of all these states, we add the change in the energy of all these states into the perturbation. So basically now my electron-phonon perturbation comprises of the electron-phonon interaction potential minus the difference in the individual energies from this mean energy. And this is basically the potential inside this particular bin. Now, just the way it happens in the case of degenerate perturbation theory, so what we have actually done here, at these states which were not fully degenerate, we have made them degenerate and made them one single state. And since these are now degenerate and one single state, I can use the degenerate perturbation theory to correct their wave functions. So basically, we now, what we do is that we diagonalize this potential or this Hamiltonian inside this small bin to obtain the eigenvectors and the eigenvalues of these energies, these states. Once we have obtained the eigenvectors and eigenvalues of these states, and since these states are degenerate, I can then form a final state as a linear combination of these states which were inside. So these degenerate states, their linear combination form individual final states. And this linear combination is dictated by this U matrix, which you obtain by diagonalizing this electron-phonon interaction potential inside this bin. However, this basis, if you just do that, it will not be complete because your entire Hilbert space spans the entire energy. So to complete your basis, what you need to do is that you need to bring in the mixing from the other states. However, from the very beginning, we say that this is my quasi-degenerate bin, and states inside this are degenerate. Once we have obtained the linear combination, we can expand them using the simple perturbation theory. So basically, this is a combination of these linear states and then the mixture from the states which were not inside this bin. And this forms the basis for my final energy states. Once we have these final energy states, which are excited states, which I form with the quasi-degenerate eigenvectors and the mixing from the other states, we can obtain the transition rate just like in the case of the direct transition by just using the Fermi's golden rule, where we calculate the transition rate between an initial state and these final states, which are obtained after this operation. And since here I gave an example for just one bin, but if you want to calculate or obtain any observable across the energy spectra, you will have to divide your energy spectra into multiple these bins, do this operation for each of them. So this is what the step 6 is, that we need to repeat the same step for all the quasi-degenerate bins. So if you want to obtain an absorption spectra for a long photon energy, there will be many bins, and you calculate for all of them. You perform the same operation for all of them. Now that was in the previous slide, the representation was simpler. Now we add the valence, conduction, and all those states, basically all the notations, and eventually the final wave function after the mixing and diagonalization will look something like this. So here you can see that it comprises of three components. First are basically your zero momentum excitations. Second are finite momentum excitation with a phonon absorbed and a phonon emitted. And then these three are basically mixtures with the states which are not inside the QD bin. Eventually, once you have these final wave functions, you can obtain, as I said, the transition rate. And this is what we get as the transition rate after doing some linear algebra. So basically performing the Fermi's golden rule. And this is the expression that you get for the transition rate. If you look at this expression, it looks gigantic and it might scare you, but it's very symmetric. And there is meaning to all these terms, physical meaning. So the first term is just the direct absorption. So basically absorption at the same wave vector. However, these A, B, C, D terms represent like multiple phonon processes that can take place. So first is the A term, where you can have a electron hole pair created at between the valence 1 and conduction 2. And from there, you basically phonon takes from conduction to the next conduction band. Similarly, we can have a phonon, electron hole pair created at a valence band and conduction band at k plus q. And then from some other valence band, an electron comes and fills this hole. And eventually, we have the same final state. The third thing that can happen is, as I said, that there is also that the electron-phonon can create an electron hole pair first. And from there, you have electron radiation, so photon emission, and eventually you create this electron hole pair at the same K point. So this is conduction valence to conduction and conduction to conduction. And in a similar way, you can have valence to conduction, and then you have created an electron hole, hole here. So from the top of the valence band, electron can jump, and eventually your final state is the same. So for the same final configuration, you can have 4 different processes which can contribute to the phonon-assisted absorption. This is what these 4 absorption processes mean. Eventually, once we obtain the transition rate, to obtain the imaginary dielectric constant, we need to take a average over the temperature using the partition function. And this is the final and the main result of this work is the imaginary dielectric constant, which is obtained for all the photon energies. Now, if you look at, again, this expression looks very gigantic. The first part is the partition function summation, where you can add the temperature effect. So it comes due to temperature. In the tutorial, we will have different flags to deal with this particular summation, which you'll learn later on. But if we keep this thing aside, what we see is that we have multiple terms. Now, if you look at the term which is in red, this term is actually the direct contribution. So contribution coming from the direct transitions to the imaginary dielectric constant. And if you look at the terms in the green, this is the contribution that is coming from the indirect transitions to the imaginary dielectric constant. And in the presence of both, so if you remember the very beginning, I asked a question that can we simply do a scalar addition of the transition rates? The answer is no, because in the presence of both, these many body states, so finite momentum and zero momentum excitations, are entangled by the electron-phonon coupling. And in that case, you need to obtain these unitary U matrices by diagonalizing the electron-phonon potential. And the transition rates are just renormalized between each other instead of being scalar additions. Another thing about the quasi-degenerate perturbation theory is, so here we apply it on optics. The theory is very general and can be applied to other problems. But here also we can see that there is one tuning parameter, which is the delta E, or the quasi-degenerate bin size. And if we make delta E go to 0, what happens is that these U's will become 1. So if you have just the indirect transition, your U will actually become 1. And in that case, you go to the perturbation theory. While in the case when this delta E goes to infinity, what happens is that even if you're in the indirect regime, you will have this entire expression. And that situation looks more like the full diagonalization of the electron-phonon matrix, or the electron-phonon interaction potential. So what QDPT does is that it gives you kind of a continuous function between a perturbation to diagonalization. And this can be controlled by delta E. And this is something also you will learn in one of the last exercises today in the hands-on. So this is the complete theory of optical absorption that we obtained from the quasi-degenerate many-body perturbation theory, of course, linear optics. Next, we apply it to materials. So we'll talk about some of the applications we did. And the first one is silicon. So if you remember, in the case of silicon, the CHBB has a dependence in the direct regime. The direct transitions cannot explain the indirect part. However, when we apply QDPT, we actually recover the spectra in the entire photon energy range. On the right, what you see is that by tuning these parameters, like one to go 1, other to go 0, we can actually obtain, to some degree, since these are still linear combinations and there are overlap elements, but if we ignore the overlap elements, to some degree, we can actually recover what contribution comes from the indirect absorption and what contribution comes from the direct absorption. And here we can see that in the regime of the indirect gap or indirect transitions, we mostly have contribution coming from the phonons. As soon as the direct transitions kick in, there is mostly the contribution that comes from the direct transitions. However, the contribution that comes from the phonons is not 0, and there is still quite a strong contribution. With this method, since it's perturbative, some degree, and it's pretty much exact. One can also obtain, as you saw in the previous presentation, that we have these fine structure, which we call as the phonon fine structure, where one explains the absorption and emission, these kinks. And with this method, you can also obtain these kinks. And here we obtain these kinks for silicon, and we match experiments. Next, we apply our method on a direct gap material. So in a direct gap material, the idea is that most of the transition actually happens through the direct transitions. So here we apply it on gallium arsenide. We match experiments quite well, but the more interesting part is the right, where we spectrally break the direct and the indirect contributions to the imaginary dielectric constant. Here, for the most part of the spectra, the direct transition dominates, like the entirety of the spectra. However, you can see that as the photon energy increases, the contribution from the phonons starts increasing, and there is a dip in the contribution that comes from the direct transition. This happens because as you go higher in the photon energy, your phase space starts increasing. So there are many more Qs to which the carriers can be scattered. And this is actually one of the signatures of that phenomenon. So even in the direct transition, direct gap materials, a significant chunk in their optical absorption can come from the phonon absorption. And finally, we apply our method on germanium, which is a quasi-direct gap material. And if you remember from the very beginning, that the current theory is unable to reproduce the photoluminescence spectra of germanium because its direct and indirect gaps are quite close. Here, using the QDPT, we very nicely obtain good agreement with the experiments. And also, again, I would say that the photoluminescence is just a post-processing that can be done on the output of QDPT. So for example, it's just a function of the imaginary dielectric constant, so it can be easily calculated. And when we do that, we obtain that the QDPT matches experiments quite well in the entire regime of the photon energy or the PL spectra of germanium. We can also find the contribution that comes from the direct transitions. And indeed, this second kink that comes in germanium comes from the direct transitions. But as the temperature goes down, this kink starts dissolving. And the reason for that is that the exponential here, the photon energy, as you lower the temperature, this exponential becomes higher. So it basically kills the any kind of photoluminescence that can come from the direct transition. So it's a steeper exponential curve. So we see this in nature, but we also find this in our calculation. So finally, so now we are in the conclusion part. There are alternate methods which can obtain the absorption coefficient in the entirety of the photon energy. So if you are not interested in very fine details, one of the best alternate method is ZG, which you already learned on Friday from Dr. Zacharias. And it's also implemented inside the EPW as a different executable. It's called the zg.x, which I've also learned. And finally, to conclude, we have developed a unified theory of optical absorption. This method is applicable in all regimes of photon energy. We have applied our method on multiple materials and obtained very good agreement with experiments. And this is an ongoing work which you see on the right, where we actually extend the quasi-degenerate perturbation theory to take into account the excitonic effects. And here we apply it on bulk MOS2. And as you can see, that in the bulk MOS2, which is an indirect gap material, the big chunk of spectra cannot be obtained by using the state-of-the-art BSZ calculations. But with the QDPT excitonic calculations, one can recover this spectra. This is an unpublished work and it's an ongoing work. Won't speak much about it. So yeah, that's all. Thank you.
Thank you very much.
I can't hear. It's fine.
Okay.
Can't hear. Very good question. So this was in my supplementary. So the larger the delta E, the more you will converge, but there will be a point where you converge. So here we converge for all these materials. And this is actually defined by a characteristic phonon energy. So highest phonon energy present in the material is the function of that. So when you will do the hands-on exercise today, you will find that there is an automated way of choosing this delta E, which does a pretty good job.
And so I have a few questions. Firstly, the energy that you collapse into, how do you select that energy? Is it the mean of all the states or the like the center of the bin? How do you select that?
Yeah, so it's actually the center of the bin. So if you bring it to the center of the bin, and if you see the expression on the denominators, if it is not center of the bin, there is a chance that you might end up, so the median is more closer to the boundary of the bin, and eventually you will face the same degeneracy issue. So it's the center of the bin.
Also, when you collapse the bins to a single energy, the states at the end of the bins, even though they may be close to each other in energy, they might be classified in different bins. So does that cause an issue?
No, that does not, because eventually you mix those states using the perturbation. So if you see, there are two things here. Yeah, so here you can see that you have the linear combination of these quasi-degenerate states, but then you mix states from the outside. So eventually you have a complete basis.
I have a question regarding the transition as the electron is on gravity function. So does phonon follow the same selection rule as electron in making the transition, electron transition to both during reaction?
Yes. So yeah, the selection rules are the same. So you have occupation and occupation, and you only move from occupied to unoccupied state. You have to conserve the momentum. That's all that comprises the selection rule. So it's the electron-phonon. So if you see, there are two things. So it's a diabatic process. So good question. It's a diabatic process that we are taking into account. So the states with extra phonon and a state with a emitted phonon, these two are actually distinct states themselves. So that's how you do the selection rule. Yes.
When you compute the direct gap for the velocity term, do you consider the anomalous Berry phase connection terms, or you only compute the direct group velocity?
Good.
In the direct transition.
So you're talking about the